Okay, wonderful. Welcome everyone to the One World seminar on the mathematics of machine learning. My name is Ricardo, and I'm one of the organizers on the board. We have a really exciting lineup of speakers and talks this term, and I'm pleased to introduce our first seminar speaker. Andrew Ilersich from the University of Toronto, the Institute of Aerospace Studies. Andrew has been working on machine learning for dynamical systems and has some expertise in various other areas, including stochastic optimization and data simulation. He is currently working with Professor Prasad Nair, and prior to that has completed a master's also at the University of Toronto with Professor Yano and Steinberg. Um, and today he's going to be telling us and teaching us about learning stochastic multiscale models of spatial temporal systems. So, Andrew, please take it away. And thank you for joining us.
Yeah, thank you very much. I'm Andrew Ilersich. I'm a PhD student at the Aerospace Institute at U of T, and I'm here to present the recent work that I've been doing as part of my PhD under Professor Prashant Nair on learning stochastic multiscale models. This talk is based on a recent poster and paper that I presented at NeurIPS last month, so if you find what I say interesting, you can read more about it in the paper. Complex dynamical systems, especially those involving fluid mechanics, are well known to demand the resolution of a wide range of length and time scales. Since energy is transferred between scales, under-resolving the state can cause the coarsened prediction to diverge from reality. Direct numerical simulation therefore requires that you have a high-resolution mesh, which can be computationally infeasible. This has led to a family of approaches that seek to reduce the degrees of freedom in the system. On related work now. Um, there are two related categories of approach here that I'll quickly go over. The first is reduced order modeling, which seeks to reduce the dimensionality of the state space by employing a projection between the state space and a lower dimensional latent space. It's then in this latent space that we formulate the dynamics, which are now less expensive to evaluate. The latent prediction is then finally mapped back to the full state space, giving us the model prediction. Traditionally, reduced order models have been formed with latent maps, usual approach being proper orthogonal decomposition, POD, so linear approach. But this isn't amenable to every system, especially advection-dominated ones. More recent research has used nonlinear mappings, including neural network-based autoencoders, to address this shortcoming, but they can still struggle with multi-scale and especially chaotic phenomena. Additionally, ROMs tend to only learn a global latent representation with no particular spatial structure to the latent space. Um, so if the problem specifications change, such as I have a simulation of a fluid flow and I add a new solid obstacle to that flow, you then need to form a completely new ROM. Closure models are a different approach. They work with a coarse grid representation of the state, and they aim to infer the effect of unresolved subgrid scales on the grid resolved dynamics. So unlike reduced order models, closure models retain the spatial structure of the state, and they tend to be more generalizable to different problem setups. Large eddy simulation, like we saw on the previous slide in the fluid flow case, is an example of a closure model. These have been traditionally formed not only with data-driven strategies, but also in purely physics-driven manners. LES goes back decades, and they've been derived from filtering the Navier-Stokes equations directly and making necessary physical assumptions to close the system. More recently, though, machine learning approaches have been applied to closure models too. And a good example of it is this recent paper by Boral et al. It took a stochastic approach to try to capture the uncertainty in the predictions. In general, though, shortcoming of closure models is that it's not guaranteed that the dynamics that govern the resolved component of the state will be Markovian. Um, the Maury-Zanzig formalism for deriving closure models shows that this is usually not the case. You have a memory term. So either you grow the uncertainty in the prediction to account for this range of possible outcomes, or you learn non-Markov closure models, which some researchers do for systems where it's feasible. In this work, however, I present a different approach that seeks to directly model the coupled macro and micro dynamics rather than only making force predictions like closure models do, making the predictions at the same resolution as the training data. So here I'll summarize the problem setting before getting into the methodology. I'll be using this fluid flow example, flow over a cylinder vortex shedding for most of the talk. We consider the setting where we're given samples of a spatial temporal field on a fine spatial grid and over a number of time steps. This data set may include multiple trajectories with different initial conditions or forcing. But for simplicity, I'm presenting the single trajectory case here. Our goal is to learn a multi-scale representation of this system. More specifically, to decompose and explicitly model the coupled dynamics of macroscale and microscale features. So unlike closure, we're not discarding any component of the state. We're trying to model it in its entirety. So now I'm going to go over the proposed framework for multi-scale modeling. The first step is to perform the scale separation between the macroscale and microscale features. Here we start with the macroscale, which is formed via a two-step process. Given a snapshot, we'll call it Y, we first apply a smoothing over space, which may be freely parameterized and learned. This is directly inspired by approaches like large eddy simulation, which is typically presented as learning the governing equations for a fluid field that was smoothed by a convolution over space and time. This smoothing removes small scale features from the field, so we're free to restrict the smoothened representation to a coarse grid without loss of information. This reduces the degrees of freedom while retaining the macroscale features. So because this is a stochastic framework as well, the smoothing and restriction only defined the mean of the distribution from which the latent macroscale state is sampled. If this probability distribution is selected to be a Gaussian, then the covariance may either be set up as a function of the snapshot Y, or it may be directly parameterized and constant. Forming the microscale state follows a similar process. Given the same snapshot, we first take the orthogonal complement of the smoothing, the residual. This is just the snapshot minus the smoothed snapshot, leaving us with all of the small scale features that got filtered out of the macroscale component. This can't be downsampled with the coarse mesh like the macroscale, however, because these features are necessarily going to be under-resolved. Instead, we then encode it into a low-dimensional latent space. In effect, this is a kind of reduced order modeling, but only with this residual microscale component. And this yields our microscale state, eta. As with the macroscale component, the microscale is sampled from a distribution whose mean is then defined in terms of the residual and encoding operations. The latent dynamics are described with a coupled system of stochastic differential equations, SDEs, with parametrized drift and diffusion terms. The drift consists of a macroscale drift, this f theta, and a microscale drift, g theta. A key motivation of this framework was to learn the coupling between macro and micro dynamics. So the macroscale drift also takes the microscale drift, the microscale state as an argument, and vice versa. The microscale drift takes the macroscale state as an argument. The coupling between macro and micro dynamics, however, is modulated with these functions phi and psi, which could be set to identity, or it may be useful to set them to something non-trivial if, for example, zeta, the macroscale, is much higher dimensional than eta. So the coupling term psi can reduce the dimension of zeta before passing that macroscale information to the microscale drift g theta and simplify the learning problem a bit. The latent dynamics here, this is presented in a general setting, but architectural choices can leverage the spatial structure um, inherent to the microscale, the macroscale state, but not present in the microscale. I'm going to get more into that later. Once the latent state has been propagated forward in time, we can decode the macroscale and microscale components. Each decoder maps their respective state component to the high resolution mesh, matching the resolution of the training data that was used to produce this model. The architecture of these decoders may be transposed from their respective encoders just for simplicity. Um, and again, note that these decoder maps define the mean of their respective distributions, from which we sample large and small scale predictions. Once we have these distributions, we have a macroscale distribution and a microscale distribution. We can combine them to obtain our final full state prediction. Now, as a probabilistic model, um, this combination of the macro and micro distributions it's a non-trivial combination. You can't just add them. I'm going to get into the specific functional form for this later on. So to summarize everything about the framework presented so far, um, starting from a full state observation, we divide it into a smoothed state and a residual state to separate the large scale and small scale features. The macroscale encoder then maps the smooth state to the coarse mesh, yielding the macroscale state zeta, whereas the microscale encoder maps the residual state to a latent microscale state, eta. By decoding the macroscale and microscale latent states, we obtain large and small scale feature predictions that may be combined to ideally recover the full state. Now, before we move on, a quick remark on how this compares to closure models. Since traditional closure modeling aims to derive equations governing only the resolved, what we're calling the macroscale dynamics, it may appear at first glance that closure modeling is a special case now of this framework that would be obtained by setting the dimension of the microscale state to 0. So the left-hand side of this plot disappears, and you only have a macroscale component. The objective in closure modeling is a little different from here, though. In closure modeling, the goal is to ensure that the predicted coarse state matches the smoothed and restricted y, not the original observation. So the ideal closure model will make a prediction that is assessed against y bar. Whereas here, even if we only have a macroscale representation when we're solving for the dynamics, we're attempting to make predictions that match the original observation at the full resolution y as closely as possible. Okay. So to distinguish this macroscale only case from traditional closure modeling, we refer to this case as an implicit scale model. It implicitly represents all scales solely through zeta and its associated decoder. The multiscale framework with some non-zero and eta explicitly models the subgrid scales through that microscale component eta, aiming for improved accuracy in representing the dynamics of fully resolved state. So that concludes the section on the framework. And now I'm going to talk about the likelihood that we maximize to train a multiscale model. Our goal was to learn a multiscale representation in terms of macroscale and microscale features. However, training our model with a standard likelihood does not necessarily ensure this scale separation. Because the microscale component is potentially a much more flexible latent encoding than the macroscale is, it's possible for the training process to maximize a likelihood like this by, for example, encoding the latent state, the entire state, in the microscale component and letting the macroscale go to zero. We therefore use a multi-scale likelihood based on the product of experts approach, which consists of two terms. The first is the macroscale expert, which attempts to capture as much of the full state as possible with only the macroscale component. The second is the microscale expert, which attempts to capture only the residual between the full state and the macroscale prediction. Consequently, to maximize both of these terms, this likelihood leads the microscale component to only capture what the macroscale is not able to. There's a hierarchical preference where it aims to capture with the macroscale first and only capture what the macroscale can't with the micro. All right. So after expanding terms with through and doing all the algebraic manipulation, we get the following log likelihood, which I'm going to go through term by term. Maximizing the log likelihood means that the first term, the macroscale residual, is minimized. This clearly leads the model to capture as much of the state as possible with only the macroscale prediction. The second term attempts to correlate the microscale prediction with the macroscale error so that the microscale only supplements the macroscale where necessary. The third term minimizes the norm of the microscale prediction, acting as a form of regularization, penalizing large magnitude microscale predictions. The last term maximizes this log det inverse covariance. So in essence, it minimizes the prediction uncertainty. This log likelihood can be viewed as embodying Occam's razor at the microscale level, maintaining that clear hierarchy. This multi-scale likelihood and the framework together are the essential components that comprise this multi-scale approach. We have a model structure that admits scale separation and a likelihood now, an objective function that enforces it. It's worth examining the behavior of this likelihood more closely, since it also describes how we combine the macro and micro predictions to obtain the final model prediction. This is our multi-scale decoder, in essence. The product of two Gaussian terms is also a Gaussian, so we can characterize this likelihood with its mean and covariance. The covariance of the final prediction distribution is symmetric in its arguments, the macro and micro covariances, and is found by this matrix harmonic mean. But the mean of the distribution doesn't have that same symmetry to it. The decoded macroscale prediction is its own term, but the decoded microscale prediction is weighed by this uncertainty matrix. If we look more closely at the behavior for different relative magnitudes of sigma zeta and sigma eta, the macro and micro uncertainties, covariances. Should I stop to look at chat?
Hi, Andrew.
Oh,
Yeah,
I'll do that
there's
at
a
the
quick
end.
question about the norms. If it's not too much trouble to interrupt you quickly, it would be great to clarify the subscripts on the norms.
Oh, sure.
Thank you.
Subscripts on the norms. Oh, so that's
I think on
oh
when you define the likelihood, maybe
oh, I see back here.
yeah.
Right, so that's just defined on the bottom there. So those are induced norms by some matrix A. And here, the matrix inside the macroscale residual is the combined covariance of the final distribution. And the matrix here is this function of the component covariances. Does
Thank
that
you.
answer your question?
Um,
Why no regularization strength? I'm not sure I understand what you mean.
Sorry, can I just quickly ask?
Sure,
Uh,
absolutely.
so what I mean is that usually you have some constant, right? That is a like a parameter that corresponds to the strength of the penalization.
Yeah,
So I don't know, lambda in which regression or whatever. So
yeah.
is there some reason why you would not want to include that, or maybe you don't need that? So it's just as simple as that. Thank you.
Right. So when you're designing a loss function directly, that's what you would do. You would apply some coefficient out front, and that would be a hyperparameter that you tune. In here, the regularization is handled automatically by, well, you're referring to this microscale norm term, I'm guessing, right?
Yes, that's correct.
Okay. Yeah, that's handled through the lambda, which comes through the relative uncertainties in the macro and micro predictions. So that's not something that we design directly as a hyperparameter. That's something that comes from the relative predicted uncertainties in these two macro and micro models.
Okay, that's clear. Thank you.
No problem. All right. I think this is where I was. Yeah, so if we look more closely at the behavior for different relative magnitudes of sigma zeta and sigma eta, we can see that if sigma zeta is much larger, so there's much more uncertainty, a much larger covariance in the macro prediction than in the micro, the gain matrix is approximately identity. So if there's a lot of uncertainty in the macro scale, but not in the micro scale, then um, this becomes just approximately the decoded macro prediction plus the decoded micro. The micro gets to have its say. Otherwise, all right, column here, the microscale contribution is diminished if the macroscale covariance is very small. So if the state is well captured with only the macroscale term. It's also diminished if the microscale covariance is very large, because that means the macroscale prediction error is not well captured with the microscale term. So in this manner, the scale hierarchy in the likelihood allocates representation capacity across scales as necessary, weighed by their relative uncertainties. So here I'm going to take a brief detour to talk about the variational inference approach that I used for training. This part is not an original contribution of my paper, but it's an important tool that made the task of training these models much more tractable. So I'm going to go a little bit into it. Let's start with a general latent SDE system, like the one we're forming for multiscale models. For shorthand, we group together the macroscale and microscale states zeta and eta into a latent state z. And we group the macro and micro drift functions into this combined drift gamma. So that just makes everything a little shorter to write. So as we went over for the multiscale framework, latent SDE models are a three-step process. First, given an initial condition from data, you sample the latent initial condition from a probabilistic encoder. Second, you solve the latent SDE system to propagate this latent state forward in time. And then you sample from a decoder distribution to obtain your final prediction, y of t. So in variational inference, you specify a variational distribution Q that approximates the posterior distribution. Like many other researchers. Archambault is one example. We choose a variational distribution induced by a linear latent SDE with time-varying terms. The matrix A and the vector B depend on these variational parameters phi, which will have to be tuned during optimization, same as the other model parameters. Since we choose a linear SDE as the variational process, if the initial condition that's provided to the system is Gaussian, then the latent system becomes a Markov-Gaussian process. And the mean and the variance of that process are governed by this pair of ODEs. So before we move on, note that this linear SDE assumption is less restrictive than it may first appear. The variational approximation here is only a training tool, and it's discarded when training is complete. The actual latent SDE model is, as we specified before, it could be neural, it could be polynomial, it could be anything. And that's the one that we use at inference time. The goal of variational inference is to minimize the KL divergence between the variational approximation, which we saw in the last slide, and the true posterior distribution. Skipping the algebra to derive this, since it's standard variational inference, this is equivalent to maximizing the evidence lower bound, or elbow. There are two relevant terms in the elbow that we'll go over here. First is the log likelihood term, which is a sum over all the snapshots in the dataset. And because this likelihood serves as our probabilistic decoder, this term is roughly analogous to minimizing decoding error in the latent mapping. The next term is the drift residual term, which is an integral over the time interval covered by the dataset. And this term minimizes the difference between the linear variational drift, the AZ plus B, and the flexible drift prior, the gamma. So in effect, it's doing a kind of velocity matching between the two drift functions. The elbow could have a third term if there's a statistical prior placed on any model parameters. For example, if you're looking for sparsity and you have a sparsity-inducing prior on theta, then that changes the formulation here, and you'll have a third term that's the KL divergence between the posterior distribution over theta and the prior. But I'm ignoring that here for brevity. So note that in both of these terms, that samples of Z are drawn from the variational distribution Q. And this introduces a computational bottleneck that I'll address next. So what makes the elbow tricky to evaluate is that obtaining samples of Z from Q of Z given T, the variational distribution, means solving the pair of ODEs for a Markov-Gaussian process that we saw earlier to obtain the mean and covariance of the distribution that we need to sample from. So this is the main computational bottleneck, especially for stiff systems, as the time marching scheme will need to take more and smaller steps. This phenomenon appears generally in neural ODE and SDE systems as they're trained and the dynamics stiffen. The training actually slows down as each loss function evaluation takes longer to perform. The time marching scheme needs to take smaller steps. There's a couple of recent papers out of my same lab. This is one of my colleagues a couple of years ago that proposed a reparametrization trick to address this issue. So by reparametrizing A and B in terms of M and S, instead of parametrizing A and B, and then calculating M and S by solving the ODEs, we can parameterize M and S and use those to solve for A and B. And this saves us the trouble of doing any time marching to obtain samples of Z. So the elbow can be now evaluated by sampling from some specified MNS with no time marching required. MNS of T, I should say. Um, and yeah, since we're now free to specify the mean and variance of the latent variational distribution as functions of time, we can choose a latent Gaussian process whose control points are obtained from applying the encoder to our data set. So this fully decouples the cost of training from the stiffness of the dynamics, and this makes it much faster to train more complex models. Next, I'm going to talk about some of the specific architectural design choices that I made to implement a multiscale model. These aren't intrinsic to the framework and they could be different, but I think they make a reasonable starting point. For the macroscale, we have two parameterized terms to specify. The first is the smoothing, which I chose to use a convolution for. The kernel for this convolution could be set to a Gaussian, for example, but I left this kernel freely parameterized, free to learn. We'll see an example of one of those learned kernels later. The macroscale encoder, which restricts the smoothed state to a coarse mesh, is accomplished here with a simple downsampling. And putting these two operations together, the map from the snapshot to the macroscale state is simply a strided convolution, where the stride is the downsampling factor between the high resolution mesh and the low resolution mesh. So for example, if your fine mesh is a 64 by 64 and your coarse mesh is 16 by 16, then the downsampling factor is 4 in that case. And the kernel size comes from some even multiple of that factor. I use k equals 2 for most of the numerical examples we'll get to later, since this ensured some decent overlap between adjacent grid cells. For the microscale, one of the terms is already defined for us. Since we have a convolution for the smoothing, the residual is just the snapshot minus that convolved snapshot. The microscale encoder, as we said before, can't just map to a coarse grid, since that would lose all the small scale features. So it needs a more flexible encoder architecture. Here I used a straightforward convolutional neural network with 4 layers to map from the fine mesh to a latent vector, same as any common autoencoder architecture for image data sets. So unlike the macroscale encoding, this loses the spatial structure by using an abstract latent space. Yeah, it captures the microscale features in a global manner. Hmm. Because the macroscale state retains a spatial structure, we can leverage this with the architecture that we choose for the drift function. I mentioned before that convolutional neural networks, you could use that for spatially structured data, and that's a possible candidate for the drift. But for this work, I use a stencil that applies a localized drift to each grid cell. So if we look closely at the figure here, take the ith grid cell from the macroscale grid, pointing to it on the left figure. The drift function at that point, the drift function for that ith component of the macroscale state, will be a function of only its neighbors. This is inspired by the spatial discretization schemes that are commonly applied to solve PDE systems. And this cell-wise drift, this f hat, is then applied in parallel to every grid cell and its neighbors to obtain the full drift over the field. Because the microscale state has no spatial structure, the drift is simply an MLP with fully connected layers that leaves it nice and flexible. So finally, I'm going to go over a few results from the paper. To assess each model, this is the process we follow. First, for training, we start with no microscale. So there's only a macroscale component to the latent state. This is the implicit scale model scenario I mentioned earlier. And once this implicit scale model is trained, I use its parameters to initialize a new model that has a 1D microscale state. I then train this model and repeat for higher dimensional microscale states. Use the trained model parameters for 1D to initialize the 2D, use the 2D to initialize the 3D, and so on. By this approach, the cost of training scales linearly with the microscale state dimension. And I found that this approach stabilized the training significantly, ensuring near monotonic improvement to the test error as n eta was increased. Without this hierarchical training scheme, I found that the lost landscape was more difficult and non-convex, and getting stuck in local minima was an issue. The error would appear to increase with n eta in some cases, even though we know going in that a higher dimensional n eta should be more expressive. But training in this hierarchical manner seems to fix that. The baselines that I compare each multiscale model to include two ROM techniques, coarse simulation, direct numerical simulation, and the macro-only implicit scale model. The first ROM baseline uses a linear POD map between full and latent states, and it learns the latent dynamics with SIMD. That is, it learns an ODE system with polynomial terms. The second ROM baseline is dynamic mode decomposition, which learns a discrete time linear map from one time step to the next. For the coarse DNS, the model that was used to generate the data is coarsened to the same grid resolution as the macroscale component of the multiscale model to try to match latent state dimensions. Likewise, the latent state dimension for both ROM techniques is the same as the latent state dimension for the multiscale model they're being compared to. The last baseline is the simplistic scale model to ensure that including the microscale component actually does reduce the prediction error compared to a macro-only representation. Finally, the model performance is assessed using this simple relative error metric that compares the observation from the data set at each time t to the mean of the prediction distribution from each model. Since this provides a different error value on each time step, I'm going to compare the statistics for this error. So there are 4 test cases that were considered in the paper. These include 2 1D cases, a simple advecting wave and the KDV equation, and 2 2D cases, flow over a cylinder and a radial dam break. For the cylinder flow, we have a velocity field. So the state contains x and y velocity components. The cylinder is represented as a region here of 0 velocity. For the shallow water equations, the initial condition is a column of fluid in the middle, which then collapses into a radial wave going out in all directions. The 2 1D cases I generated are from numerical PDE solvers, whereas the last 2 cases are the last 2D cases are from public data sets. There's more detail in the paper about all of these. For the results here, just for time, I'm going to focus on these 2 cases. Since I mentioned before that the macroscale smoothing kernel was learned, let's take a look at what kind of kernel it learns. For this example, I'm using the cylinder flow case, and I'm looking at how the kernel smooths the x velocity field. The learned kernel is very smooth and nearly Gaussian, you can see here, but not quite. It does have some negative regions above, below, beside the main hump in the middle. If the kernel of the convolution was simply chosen to be Gaussian, then this smoothing would amount to a low-pass filter. Because we leave the kernel learnable, we may discover that the optimal kernel for a given case is non-Gaussian. It may even introduce, some small-scale, high-frequency features if the kernel chooses. We can also see that if the optimal kernel is close to Gaussian, the training process is capable of discovering that. So in any case, a trainable kernel is a negligible addition to the parameter count of a multiscale model, so there's no reason not to do it. We can see here how the state is modified by the smoothing, restriction, and prolongation using this kernel. The d zeta the last step that prolongs to the full mesh, is the transpose of the convolution that has this kernel. And yeah, we can see the smoothened state and especially the macroscale state on the coarse mesh. We lose the small scale features present in the original snapshot, but the learned kernel somewhat reintroduces them in the prolongation. And if the kernel had even more high frequency features present, if it wasn't so smooth, then this would be even more pronounced. But it is possible, though not that present in this case. Next, we have a visualization here of what the scale separation looks like for the learned multiscale model in cylinder flow case. The full state here is on a 320 by 80 mesh, and it's coarsened for the macro scale to 32 by 8. We can see how the vortex structures that are unresolved by the macroscale state are captured by the microscale. And notably, as the vortices grow larger and propagate to the right of the domain, the microscale contribution diminishes, showing how the model is able to adaptively allocate representational capacity across scales as needed. So since we formed a stochastic model, we can compare not only how well its predictions match the observations from the data set, but also how well its uncertainty matches the true error in the solution. We can quantify the prediction error later. This slide provides a visual comparison to start with. The model prediction here is perfectly capable, we could see, of capturing small scale features that would be lost in implicit scale or closure models. And the absolute value of the error between the observation and the prediction is well anticipated by the standard deviation bounds. So next, this is the shallow water equation radial dam break example. And this animation hopefully clarifies what that radial dam break looks like. The full state is on a 128 by 128 mesh, and it's coarsened to an 8 by 8 for the macro scale. The coarse grid structure of the macroscale prediction is especially evident in this one, and it's utterly unable to resolve the sharp circular shape of the wavefront. The microscale component is able to round out the shape and hide the grid structure somewhat, but its largest contribution is to resolving that sharp change in the water height at the wavefront. So let me start that again. As with the cylinder flow, we could see that as time passes and the state smooths out, the microscale contribution is diminished. It's greatest at the initial condition and goes down over time, as the macroscale is better able to represent the full state. So, like with cylinder flow, we can compare visually the prediction quality as well as the uncertainty. Note here that there's this high error ring at the initial condition that diminishes with time. This is because, unlike the cylinder flow example, which was a single trajectory data set, this one's multiple trajectory. And what's different about each one is that they have different initial conditions. Those different initial conditions are different radii of the column of water in the middle. And that's something that's very hard to encode in latent state, especially because it's a binary field. So that does tend to get smoothed over as the model represents that, and that's the biggest source of error here. But as the water spreads out and that sharp boundary gets smoothed, that error diminishes. So here we give a bird's eye view to the results. More details can be found in the paper. So across all 4 test cases considered, a multi-scale model with a 5D microscale state is compared to all the baselines discussed earlier. The paper also contains an ablation study where the microscale dimension is varied between 1 and 5, so refer to that if you're interested. Since I didn't get into the 1D cases here, I'm going to briefly gloss over them. The KDV system and especially the wave are advection dominated, making them ill-suited to the linear ROM approaches benchmarked here. and the direct simulation via spatial discretization suffers quickly when the resolution is as coarse as the grids we've been using here. For the cylinder case, since this one is not as heavily advection dominated, the baselines perform much better, especially DMD. This isn't surprising as it's a periodic system, and the latent state dimension is generous for DMD standards. The multiscale approach is able to take advantage of this as well, leading to sub 1% error. The shallow water equation case is trickier, partly for why I mentioned before, and also because it is advection dominated. And the wavefront is under-resolved by many coarse representations. This makes the microscale correction utterly necessary, as we can see that the mean error in every other baseline is roughly half an order of magnitude worse. So in sum, we could see that explicitly modeling the microscale state improves error by nearly an order of magnitude in some cases compared to the macro only, and consistently outperforms other baselines. So before finishing with the results, here's a comparison of the multiscale models with baselines in terms of both mean relative error and online inference cost. To get around variations in hardware or implementation of each method, the proxy for online cost used here is the number of function evaluations times the latent state dimension. All the baselines are shown, and for the multiscale approach, it shows the range of outcomes depending on different microscale dimensions. It also shows the cost of doing a full DNS with a vertical line on the right of each subplot. Although the multiscale models are more computationally costly than most baselines, this is often made up for with significantly improved error, and it's still much less costly than full DNS. Additionally, increasing the microscale dimension does not appear to consistently increase the online cost of these test problems, both because the microscale dimension is much smaller than the macroscale dimension on these problems, and because the microscale dynamics do not substantially stiffen the system compared to the macro alone. So that concludes the contributions of the research I presented at NeurIPS. It looks like I'm a little short on time, so maybe I should skip over future work.
Thanks, Andrew. Feel free to, we still have a few minutes. It's up to you if you want to save some minutes for questions, but also if you want to just briefly hear about it. Oh yeah, Han is saying that he would like to hear your future work.
Oh, okay. So first one is for multiscale in time. Here in this work, I presented a multiscale framework that separates high frequency from low frequency features in space, but it could be extended to temporal multiscale modeling as well. By time averaging high frequency behavior in the system, this can potentially reduce the stiffness in the system and reduce the inference cost in turn. So here's an example of what that might look like. The Fitzhugh-Nagumo model is a common stiff toy problem used to model excitable systems like neurons, and it's a common benchmark for implicit time marching schemes. Because this is an ODE system, there's no spatial dimension reduction to be had. But if we perform our scale separation in time, we obtain a macroscale component with shallower jumps and a microscale component that looks like little wavelet corrections. By itself, this may not save any cost or de-stiffen the system, but if the error is acceptable, then this may be an approach to learn macroscale-only dynamics, closure style, that are computationally cheaper than the full system. This is still something I need to explore more deeply, so this is just a what if right now. The more meaty future work is the extension to chaotic systems. The results I presented show that multiscale works well for non-chaotic systems. However, the methodology, as I showed, is not easy to apply as is to chaotic systems like turbulent flow. This requires further methodological refinements to help the framework scale better. First is that the latent space representation of the microscale component is not easily extended to chaotic systems, as the necessary microscale dimension is going to grow sharply. So switching from this to a spatially structured microscale is an important step. Next, the likelihood, which is currently formulated to minimize error between each prediction and observation, is not well suited to capturing long-term statistical behavior. It's especially known that this kind of error minimization, like I've been doing, can lead to spectral bias for chaotic systems. High frequency modes are inherently harder to model, so minimizing MSE or doing max likelihood of the error um, tends to produce models with a low frequency bias. Um, Finally, although the stencil drift architecture worked well for non-chaotic systems, chaotic systems may require alternative drift architectures, and all these improvements are in the works right now. This animation that I'm showing here is a preliminary result on a turbulent flow. It's not ready for publication just yet, but it's in the pipeline. Last thing before I close off, before I end today, I'm going to talk a little bit about a software package I put together for learning latent SDE systems by variational inference. The present works code base and another upcoming reduced order modeling paper are both based on this package. It's built to be reasonably modular and general purpose, and it implements the simulator-free approach that I had taken a tangent to discuss earlier. It streamlines the process of setting up and training the model. As you could see with the example code on screen, you supply it with models for the encoder, decoder, drift dispersion, log likelihood, and latent distribution, as well as give it the time series data. And it handles the elbow calculation and training process. So that's available online if you're interested. Well, that concludes this talk. Thanks everyone for attending. And if you're interested, additional details can be found in the paper. And the code and examples are available in the associated GitHub repo.
Thank you very much, Andrew, for the nice talk. So we have a few minutes briefly for questions, and we actually already have one in the chat.
Yeah, I see that. So let's go back to,
Maybe I'll just repeat it in the meantime.
yeah.
So Daniel asks for the decoded macroscale and microscale states from the shallow water problem. There are some weirdly square features given the radial symmetry of the problem. Do you think this is a product of the square grid discretization or something else?
Yeah, that's absolutely it. It's because of the square grid discretization. What the macroscale is doing, it's a little easier to see with the, yeah, here, this slide. Um, how the smoothened representation comes from this coarse grid representation. Um, I don't have a slide for that with shallow water, but the same thing is going on. This macroscale state is decoded from an 8x8 representation. So that's what makes it so square.
Awesome. Thanks, Andrew.
Any other questions?
Maybe while people are thinking, I'll also ask, I was wondering in all of your one question that always comes up is choosing the latent dimensions in the architectures. And I was wondering if you had any strategies or criteria from your framework that could be used to choose the latent dimensions.
Yeah. Um, well, so in this model framework, you have two to choose, right? You have the macro and micro. For the macro, because at least for these problems, the macro dominated. So with the shallow water here, since it's on an 8x8 grid for the macro, that's a latent macroscale state dimension of 64. Um, and the microscale is only varied from 0 to 5. So um, choosing the macroscale is going to be a matter of computational convenience. How much can you get away with? Because that comes as close to a direct treatment of discretizing and modeling the original physics as possible. The macroscale dynamics could even be conditioned on the known dynamics if you have access to them. Um, for microscale, it's a matter of, at least as I practiced it for these problems, increasing the microscale dimension until the error got as low as you wanted. Or if you're dealing with a bigger problem, you're upper bounded by computational costs as well. So with microscale, you would start with it low, maybe even start with it 0 and increase as much as necessary. With macroscale, start as close as you can to the original resolution, bring it down until it's something that's tractable.
That makes sense. And
Yeah,
so I presume it's basically like starting just at the macro scale with the
yeah,
micro scale set to zero, the
yeah,
dimension, and then kind of it follows your same training strategy of training first the macro scale um,
yeah,
before training the micro scale. That makes a lot of sense.
yeah. Part of the reason I did this way wasn't just for stabilizing the training. It's also because if you're in the real world trying to use this to model some method, you're not going to know going in what the necessary dimensions are.
That makes sense. Thanks, Andrew. Any other questions?
It's 1 o'clock, so I think everyone wants to run.
Yeah, so maybe with that, I'll just please join me in thanking Andrew again for the very nice talk. We appreciate it very much, Andrew. We'll see the recording on YouTube, and feel free to get in touch with Andrew if you have any other questions. We'll also have our next seminar in 2 weeks on the 28th of January. I look forward to seeing you all there. Thanks.
Yeah, thank you all very much for coming.